Hi everybody, it's Miss Billingsley. Today I wanted to go over the Algebra 1 launch problem with you. So it would be a great idea to go ahead and pause this video and find your answer sheet. It should be in your notebook somewhere. If you don't have an answer sheet, hopefully you've been keeping up with your launch problem answers somewhere. So go ahead and find wherever that is. Okay, as you can see here, I have my launch problem on hand because we're going to be answering questions 1 through 8. So another thing I have handy is my data, as well as the graphs for the flu and the coronavirus. So I have all of that ready to go, and we'll just go ahead and jump right in. So on number 1, we are asked to use data and the data provided in Desmos to create a best fit quadratic function in vertex form. So the data that this is referring to is here, this 2019-2020 season flu data. So we provided this to you and then gave you a template to use in Desmos. So I'm going to jump over to that. As you can see here, I've already entered the data here in the left-hand column. As we do that, this box right here changes values. So the more data that we add, it gets more and more accurate, and it actually spits out the percentage that it's accurate. So this one, the statistics here, our squared value is 0.86, which means that this data is 86% fit to the red line that we see here. So it's an 86% fit, which is pretty good. We're actually going to use this graph to create the vertex form. So what it gives us here are the A, B, and C values. We don't want A, B, and C values. What we want are just the A value and the vertex. So by tapping on the graph, we see that vertex there at 41, 129,614. And then over here on the left, we see our A value is negative 73.32. So I'm going to pull that data back over here into my answer sheet and go ahead and write that here. So f of x equals, my A value is negative 73, and then vertex form takes x minus h, which was 41 squared, and then I can't remember the other data, 0.129614. Okay, and that's the k value there for our h and k from our vertex. So, awesome job. That is number 1. This is the predictive model. Notice that I didn't use the decimals because here we're talking about people and weeks. Decimals would be appropriate with weeks, so if you put decimals there, that's fine. But remember, we don't have part of a person, so I'm not rounding. I'm not using decimals on my k value here. Okay. So now let's take a look back at our launch problem and look at number 2. Number 2 asks us to use that model that we just created using Desmos to predict when the flu the number of flu infections will reach its peak. Okay, what is the approximate maximum number of flu infections this season? So I'm going to jump back to the graph really fast. Notice that the word peak is another way to say maximum. So when does the season hit its maximum number of flus? And at that point, how many are there? So we can actually use the numbers from our vertex for this. Okay, so that peak occurs at the vertex, 41, 129,614. Okay, what this means in context, which is what we're looking at here, we want to write a sentence about what this means. So after 41 weeks, the maximum number of flu infections reaches its peak. With 129,614 cases. Okay, so because my y value represented the number of people that was given to us in the entry doc, and our x value was number of weeks, that is how I know that after 41 weeks, there will be this many people that have had the flu. Now, that doesn't mean they still have it. That is just how many people have had it at that maximum point. Okay. All right, let's take a look at number 3. Number 3 asks us to approximate how long the flu season will last according to our model. So how long is an indicator that we're wanting to look at time. And time in this situation is weeks. So I'm again going to jump back to my graph and take a look at weeks. Now remember, weeks was the x-axis. So we're looking here for the start and the end of this flu season. And in this case, what it's hinting at is those zeros. So I'm clicking on my parabola here. Remember, Desmos gives us all of these key features, all of these important numbers, just by clicking. So notice that the first 0 is back here at -1. What that means is that flu season started before the first reported case. Now, remember, this is just a predictive model. It's only 86% accurate. It's not 100%, so we can't necessarily count on this for everything. But according to this model, the flu season started a week before. Now, that doesn't really make sense, so what I'm going to use is 0. Obviously, it started at week 0. The first person to report it is that week 0. And then it ended over here at this 0, 83.075 weeks. So jumping back to my answer sheet, I am going to say, so we're interpreting using a sentence. The flu season lasts approximately 83 weeks. And I'm going to make a note here that is since the first reported case. At week 0. Okay, so about 83 weeks. If you know anything about time, you'll know that a year has 52 weeks. What this means is that a flu season really never ends. It continues and continues and continues. There's a small amount of people that have the flu all year long. So these flu seasons do overlap, but the amount that is overlapping is quite small in comparison to the peak of the flu season. But again, remember, it's just an approximation, so it's not 100% accurate. Okay, we're moving right along. Let's take a look at number 4. For this scenario, what do the key features of domain, range, increasing, decreasing, positive, negative, and zeros represent? So basically, we're asked to interpret each of the key features. Let's start with domain. Okay, remember, domain on a graph is from left to right. So if I'm looking left to right on this graph, I do notice that it does continue to infinity. If I zoom out, those legs would continue down forever. But because this is a context problem, it does kind of have endpoints that we're looking at. And it actually coincides with the last question. If we're looking at the x-axis, those zeros represent the start and the stop of the flu season. So from 0 to 83 represents the approximate length of flu season. Okay, now range is looking from bottom to top. So again, I'm looking back at my graph and looking at the y-axis this time. Remember, y represents the number of cases. So the lowest number of cases we can have here is 0, and the maximum number of cases that this model shows is that y value of our vertex. So technically, according to our model, the range goes from 0 to 129,614. Had to check that number there. So this is the approximate number of cases. Okay, so the approximate number of cases in a flu season, in this previous year's flu season. Okay, we also want to compare, sorry, I need to double check what those other things were. Increasing, decreasing, positive, negative, zeros. Okay, so increasing, let's take a look at increasing. On my graph, increasing is any sections that I see going uphill. So for us, I see all along here going uphill right until we get to the vertex there. So it's increasing, and remember we use x values for everything except range. So starting over here at 0 and increasing all the way up to that peak of 41. So from 0 to 41. And I'm using these included bars because it's in context. We can't go any further than 0. We can't have any negative weeks. So I'm using these brackets to indicate that. So it's increasing from 0 to 41 weeks. So the number of cases is growing. Okay, so that growth is shown by the increasing portion, and in comparison, the decreasing portion is going to be from 41 weeks from the peak to the end of the flu season, which we said was about 83 weeks. So this would show that the number of cases is decreasing, or I don't want to use decreasing in the definition of decreasing, is we'll just say are falling. Okay, and then let's take a look at positive and negative. Okay, so positive is anything above the x-axis. So again, just looking at the x values above the x-axis, I noticed that all along here, everything through 83 weeks is above the x-axis, all of these values. So we can say from 0 to 83 weeks is positive. These are confirmed cases. So anything above the x-axis is a confirmed case. Negative doesn't really make sense in this context. We can't have negative infections. So I'm going to say NA. No negative infections possible. Okay, and the last one I'm going to squeeze in right here are the zeros. Okay, and the zeros we saw were at -1, 0, and at 83, 0. These represent the start and the end of flu season. Okay, we said that this negative doesn't really make sense. So if you put 0 there, that is fine. Technically, it is at -1, 0. So I'll go ahead and leave that there just to be technical. Okay. All right, that one took us a little while, so if you need to pause here and check your work, go for it. Okay, the next one is number 5, and on number 5, we are going to calculate and interpret the average rate of change between 20 and 30 weeks after the start of flu season. So what I'm going to do here, since I can't pull my graph into this PDF, is get those data points, and I'm actually going to make a table and find the rate of change, which is just the rise over the run. Remember, it's not really slope, but we're averaging all of the slopes between every single little point in this interval. So we're looking at the interval from 20 to 30 on our graph. So I'm going to need those values from my Desmos here in just a sec, but I'm going to go ahead and prepare the table with my X and Y values. We need 20 and we also need 30. Okay, so looking over here, I'm just going to scroll along my red line until I find 20 exactly. There it is. So, oh, sorry. It's hard to stay put with a dog in your lap. 97,188.55. I'll go ahead and round that up. No, I won't. That's people. 97,188. after 20 weeks. And then we're going to do the same for 30. 120,000, where did it go? 694. 120, 694. Okay, very good. So we have our table all filled out here. What I want to do is find the difference between them. So I want to find the delta x and the delta y here. So I'm going to grab my calculator, and the way that I can find that is by subtracting backwards. So here we get plus 10 for our delta x. And 23,506 for the delta y. Okay, so after I've found these values, what I want to now do is find the rise over the run, or in this case, the delta y divided by the delta x. This would be the same as going on the graph and counting how many up and over, but in this case, because they are such complex numbers, this is probably the simplest way to do it. Okay, so we'll put our delta y on top, so that 23,506, and then divide that by our delta y, which is 10. So the rate of change here over the interval from 20 to 30, and I'll go ahead and put an equal sign there, is going to be 2,350.6. Okay, so that is us calculating it. Now what we're wanting to do is interpret it. So use a sentence to tell what this means. So we'll just write a brief little sentence. The rate of change, we're taking the number of infections divided by the number of weeks, because Y is infections, X is weeks. So what this means is that on average, between weeks 20 and 30, $2,350 people get the flu each week. Okay, so on average, between weeks 20 and 30, 2,350 people are getting the flu each one of those weeks. So for 10 weeks, that is the average. Okie doke, we are more than halfway there. We've got a couple more to look at, and all of these involve the coronavirus data. So we're all done with our flu data. Now I'm going to pull up that coronavirus graph that was provided to us. So right here, we'll take a look at that coronavirus data. It was given to us in graphical form, so a little bit different than the flu virus data, but still same approach, and we just have a couple different questions. The first one is writing the equation for this graph. We're only given the graph itself, and we are told to write the equation for it, which is one of our standards. So the two things that we need in order to write a vertex form equation are, of course, the vertex as well as the a value. And notice here the a value isn't super explicit. So what we're going to have to do is actually find the a value. If you can remember back to class, we talked about this normal pattern that normal parabolas have. So when a is 1, there's a pattern between the y values of 3, 1, 1, 3. So if we look at the vertex is kind of here in the middle. And if we look at the two neighbor points on both sides, they would have this pattern. So what we need to do in order to find the pattern here and what the a value is find the difference between these 2 points. So between 12 and 13. So I'm going to make a little table over here. Oops. With my X and Y values. So at 12 weeks, we have 550 50,000 people with the coronavirus. After 13 weeks, 546,000 people. Remember, these are just predictions. And down here we can see since this data was pulled on March 2nd. So it probably has changed a little since then, but that's okay. Okay, what we want to look for is the difference between these 2 points. If it was normal, they would just add 1, but this is definitely not normal. There's much more added here. So if we take a look, this one is actually subtracting 4,000 in between these 2 points. So instead of 1, that number has been multiplied by what? What can we multiply by 1 to get negative 4,000? Very good. It's negative 4,000. And what that means is that our A value here is negative 4,000. Okay, so now we have everything we need to write our equation for number 6. So let's jump back up to our answer sheet. So we're going to write our equation, and I'm going to use f of x, or a function that produces this graph, and our A value is negative 4,000. Okay, and then we're going to use our vertex, x minus, of course I don't remember it, 12, 550,000. Okay, so x minus 12 squared plus 550,000. Remember, these values were our h and k from our vertex, and our A value was calculated, negative 4,000. Okay, so this is the function that we're going to use to answer numbers 7 and 8. Okay, so on number 7, whoops, I kind of skipped number 6. We'll highlight it here. Number 6, we wrote the quadratic function in vertex form that represents the coronavirus graph. Now what we're going to do is interpret the meaning of the vertex. How is it the same or different from that of the flu model? Okay, so interpret the meaning of the vertex. Again, we see that word interpret. We're really practicing our interpreting. So I want to use the words from the problem in a sentence that tells me what this vertex means. So luckily, the x and y values have the same meaning for this as it did the flu. So we're not really having to do anything crazy, except remember that the x value is the number of weeks after March 2nd. So our vertex here is 12, 550K. I'm going to erase that second comma so I don't confuse us. Okay, and what I want to do is interpret this. So what this means is 12 weeks after second, and I'm going to actually add approximately since it's just a prediction. Approximately 12 weeks after March 2nd, it is predicted that there will be 550,000 Americans since our data was just from the US. That is not how you spell Americans. With, let's just say COVID-19. Okay, so approximately 12 weeks after March 2nd, there will be approximately this many Americans that have COVID-19. I did not switch colors, so I'm going to do that now. All right, nice lime green there. Okay, so that is our interpretation of the vertex. That's what this means. Now, again, I know we're getting really close to having that many people, and I don't think we've quite hit the peak yet. So this is not a perfectly predictive graph. This data comes from over a month ago. So over a month ago, we were expected to peak, very soon. But now that data has changed just based on more information. So again, not perfectly accurate. It hardly ever is with statistics. So we'll just kind of keep that in mind. I want to make sure that we've answered that question in its entirety, and I don't quite think we have. So On number 7, we're interpreting the meaning of the vertex. We've done that. How is this the same or different from that of the flu model? So remember back on number 2, we did the same exact thing where we interpreted the flu. And let's kind of look at the differences. So looks like the coronavirus data is growing much faster. So in a shorter amount of time, there are much more people with the virus. So growing faster it also has more total cases. So there are much more cases than there was of the flu, and we kind of knew that. They don't quite behave the same. So any other things you want to include in that comparison are great, but we're going to get more into that on number 8, our very last question, where we actually go into depth comparing the two models. So on my Venn diagram down here, I'm going to go ahead and label my 2 different sides. Let's call this side the flu and this side the COVID-19. Wow, that was horrendous. That's better. Okay, and then of course in the middle are what they have in common. Let's start with that. That seems pretty easy. There's not a whole lot that these have in common. So if I'm looking at their graphs, one thing I notice, or if we also can look at their functions up here on numbers 1 and 6, one thing I notice is that they both have a skinny width. And that just means that A is greater than 1. Okay, so they both have an A, or an absolute value of A, that's greater than 1, which makes them both skinny. If we were to look at this all the way zoomed out and not so zoomed in, they would be super skinny because of the rate of growth. They grow quite fast. So another thing that I notice is that they both open down. Okay, they both open down, which means that they both have a maximum. Okay, so they both open down, both have a maximum. One more thing that I noticed is that they both can never be negative. So they both in context can't be negative. If we weren't looking in context, we could also add domain to this same list because all quadratics have the same domain when not in context. But in these cases, they don't have the same domain because of the restriction. So remember, our domain from the flu was from 0 to 83. And our range for the flu was 0 to 129,614. Okay, over here on COVID-19, we have not found those things yet, but we sure need to. So let's take a look. We can find some of these from our vertex points. So for our range, I know that it goes from 0 to 550,000. Okay, but the domain I don't know, so let's go ahead and look back at our graph. My domain is from left to right, so I'm looking from this left point 0 to this right point 24. So from 0 to 24 weeks. That means approximately 24 weeks after March 2nd, no one will have the coronavirus. So again, not sure if that's true, but that is what this predictive model says. Okay, some more things we can include here are increasing, decreasing, positive, negative, and we found all of those over here on number 4. So I'll go ahead and copy those over. The increasing values were from 0 to 41 for the flu, decreasing from 41 to 83. Okay, positive intervals were from 0 to 83, just like the domain. And again, neither of these can be negative, so we won't include that. Over here on our COVID graph, increasing, decreasing, and positive. I know that all the way across from 0 to 24 is positive, and that it increases from 0 to the vertex, which was at 12 weeks, and then it decreased from 12 to 24 weeks. Okay. So they have a lot of differences. There's not a whole lot that they have in common. Let's double check our list and make sure we have everything that we need to include. One thing I don't see are the zeros, which we found over here on number 4. So the zeros here were at -1, 0, and 83, 0. Over here, our zeros were at 0, 0, and at 24, 0. Okay, so neither of those are the same. Okay, I think that about covers everything. If there's anything that I left off that you're unsure about or have questions about, please email me or Miss Martinez, and we will definitely get back to you. But for the meantime, I think that is all for now, and what great timing. So any questions, shoot us an email. If not, we will see you on the flip side.